In this section, we explain how to calculate the reaction forces. When a concentrated force with a horizontal component acts on a simply supported beam. A simply supported beam is a statically determinate structure with 3 reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in 3 directions. For an object at rest, equilibrium in all directions is required. The simply supported beam, to be discussed, has a roller support at point A, a hinge support at point B, and a length of L, as shown in the figure. We will determine the reaction forces when a concentrated action force P with a horizontal component acts at point C, which is located a distance A to the right of point A or a distance B to the left of point B, as shown in the figure. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely in the horizontal and rotational directions, but it restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. Step 1. Create a free body diagram of the reaction forces. The roller support at point A restrains the vertical movement of the beam, so the reaction force at point A is given by the vertical reaction force VA that restrains vertical movement. The hinge support at point B restrains both the vertical and horizontal movements of the beam, so the reaction forces at point B are given by the vertical reaction force VB that restrains vertical movement, and the horizontal reaction force HB that restrains horizontal movement. The directions of the reaction forces are assumed as follows: VA is upward, VB is upward, and HB is leftward, as shown in the figure. Step 2. Determine all the reaction forces by applying force equilibrium in the 3 directions. First, decompose the action force P into its vertical and horizontal components. Create a rectangle with the action force P as the diagonal. The directions of the 2 orthogonal sides of the rectangle should be aligned with the directions of the reaction forces, namely the vertical and horizontal directions. From the sides of this rectangle, the magnitude of the vertical component of the action force P is the square root of 3 divided by 2 times P. And its direction is downward. The magnitude of the horizontal component is 1/2 of P, and its direction is rightward. Since we are dealing with forces, always verify both the magnitude and direction. Additionally, for the 3 components of the force, be sure to check the point of application as well. We will now analyze the equilibrium of forces in the vertical direction. Refer to the free body diagram of the reaction forces for the vertical forces. The vertical forces are V at point A. The square root of 3 divided by 2 times P at point C. And VB at point B. We will derive the equilibrium equation for these forces. In the vertical force summation, forces acting upward are considered positive. Let's clarify this. The force at point A is upward, hence plus VA. The force at point C is downward, hence minus the square root of 3 divided by 2 times P. And the force at point B is upward, hence plus VB. To achieve equilibrium of these vertical forces, their algebraic sum must be 0. This concludes the discussion on vertical forces. We will now analyze the equilibrium of forces in the horizontal direction. Refer to the free body diagram of the reaction forces for the horizontal forces. The horizontal forces are 1/2 of P at point C and HB at point B. We will derive the equilibrium equation for these forces. In the horizontal force summation, forces acting rightward are considered positive. Let's clarify this. The force at point C is rightward, hence plus 1/2 of P. And the force at point B is leftward, hence minus HB. To achieve equilibrium of these horizontal forces, their algebraic sum must be 0. This concludes the discussion on horizontal forces. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action for VA. The line of action for the square root of 3 divided by 2 times P. The line of action for 1/2 of P. The line of action for VB. The line of action for HB is the same as the line of action for 1/2 of P. Next, select the center of rotation. Choosing a point through which as many lines of action of the unknown reaction forces pass as possible will simplify the calculations for determining these reaction forces. In this case, we will select point B, through which the lines of action of the unknown forces VB and HB pass, as the center of rotation. Then, calculate the shortest distance from each line of action to the center of rotation at point B. This shortest distance will serve as the moment arm length for each force relative to the center of rotation. The arm length for the force VA is L. The arm length for the force, the square root of 3 divided by 2, multiplied by P, is B. Since the line of action of the force 1/2 of P passes through point B, the arm length is 0. Since the line of action of the force VB also passes through point B, the arm length is 0. Similarly, since the line of action of the force HB passes through point B, the arm length is 0. We will derive the equilibrium equation for these moments. In the summation of moments in the rotational direction, clockwise moments are considered positive. The center of rotation is point B. Let's clarify this. The force V acts clockwise around the center of rotation, hence it contributes plus V multiplied by L. The force, the square root of 3 divided by 2, multiplied by p, acts counterclockwise around the center of rotation, so its contribution is minus the square root of 3 divided by 2, multiplied by p, and then multiplied by b. Since the arm length of 1/2 of p, with respect to the center of rotation is 0, its contribution is 0. Since the arm length of Vb with respect to the center of rotation is also 0, its contribution is 0. Similarly, the arm length of Hb with respect to the center of rotation is 0, so its contribution is 0. To achieve equilibrium of moments, their algebraic sum must be 0. This concludes the discussion on rotational equilibrium. Through the equilibrium of forces in 3 directions, the reaction forces Va, Vb, and Hb are determined as follows. The calculated signs are based on the free body diagram on the left. The positive sign of Va indicates that this reaction force acts upward, which is consistent with the vector assumed in the free body diagram. The positive sign of Vb indicates that this reaction force acts upward, which is consistent with the vector assumed in the free body diagram. The positive sign of Hb indicates that this reaction force acts leftward, which is consistent with the vector assumed in the free body diagram.